Okay. Any changes in program since a few more people walked in? So our plan was to finish one or two exam problems and then discuss momentum and then maybe go back to the exam. Shall we discuss momentum now? Is it okay? Okay. So momentum is really something that gives you a feel for how much impact an object has when it hits you or hits something. Very roughly speaking. Okay, so for example, let's think of some sort of a baseball that somebody is the fielder is trying to catch. So instead of the baseball, if you had some massive ball of steel, then obviously the impact on on the fielder would be terrible. And again, if the batter gave it a much higher speed, then once again it would hurt, or it would hurt more. In fact, the fielder has to move back, right? He has to pull his hands back to reduce the impact. But suppose you were just stopping a baseball like this. Then if the ball were more massive, then it would hurt you more. And if the ball had a much higher speed, it would definitely hurt you more. So in that sense, so whatever we define as a quantity of motion, or how much something would impact, you, that quantity should really be proportional to both mass and velocity. Okay, so we call that momentum. So momentum is sometimes the definition for, or the, momentum is a measure of, people say, quantity of motion. It has, for some strange reason, the symbol P and is m times v. It's a vector. Because v is a vector, you can turn this into a vector. Okay, so how much impact in this direction? In some sense, if the ball was coming this way and I held my hand, like it just grazed my hand like that, sure, it would hurt me because of the friction and the kinetic energy, but it won't hurt, the impact of the ball will not be on my hand in some sense. So it's a direction quantity. It has a direction, so it's a vector quantity, you define it. Now, you can rewrite Newton's second law as follows. And if the mass is constant, I can pull that inside and write it this way. In fact, this is the correct version of Newton's second law, even if the mass changes. Is that true? Is that true? Is that true? Yes, that's true. Yes. This is the actual version of Newton's second law. So Newton's second law is really saying that the rate of change of the momentum of the system is equal to the net force acting on the system. So force causes a change in momentum. Okay. So if there are no forces in an object, this quantity of momentum is constant because it cannot change. The rate of change is 0. If forces act on a system, then the momentum changes, and the rate of change of momentum is given by the force. So, so that is Newton's second law. Now I want to cast this in a slightly different form, or well, it's just quite kind of stupid at first look. I mean, let's just integrate this, okay? Doesn't need an underline. So I'll integrate both sides with respect to time. Now what is this integral? You know, it's just integral dp from upper limit to lower limit. So let me integrate from some initial state, so some final state on both sides. And this gives me the net force acting from the initial time to final time of some process. Okay, so suppose the forces are acting on this for some amount of time. Then this side tells me that this is P final minus P initial. So it tells me that the change in momentum is equal to the integral of the force acting over the duration of time. So if in some duration of time, if I know the force acting, I can calculate the change in momentum. Nothing profound has happened. We have just integrated Newton's second law to find change in momentum. Okay, this should all be vector signs here. Okay. So this quantity on the left is sometimes called, impulse. So impulse, I don't know what's the symbol for impulse. I don't know what your book uses. Does anyone know? Anyways, so unimportant that nobody really cares. I've seen people use I, J, all sorts of things for impulse. It's just the integral of force over some window of time. Okay. So in some sense, this is so. Yeah, well, that's all it is. There is nothing more to it. And this is equal to the change in momentum. This is sometimes called the impulse momentum theorem. Okay. Nothing profound has happened. You have just integrated Newton's second law. So just like we had the work energy theorem, which said that the net work done by a force is equal to the change in kinetic energy. This tells you that the net change in that net impulse delivered by a force is equal to the change in momentum. Okay. So this is one more of those integrated rules, okay, integrated laws, where you have to apply it between 2 points. So yeah. So why is this useful? Well, it's the notion of impulse is helpful because some forces are such that they act over a very short period of time and their value is really high. For example, if I hit something to stop, okay, if I hit this wall, then so far no force, no force, no force, no force, no force. The moment I hit the wall, there's a huge amount of force acting on me because the wall is incompressible, right? And my hand had some speed. So the wall wants to quickly bring my speed down from v, with which I hit the wall, all the way to 0. So it needs a really high acceleration, right? And because the wall is rigid, it will supply a very large force. So that force is going to be very large, and it will be hard to calculate any details of that force. For example, that force will probably increase, will ramp up like this because my skin is slightly compressible. Now, the force will probably ramp up like this and fall down. Actually, let me write that on the screen so that everyone knows what I'm talking about. So we call this an impulsive force. So impulsive forces are those that have very high magnitude, but act over a very short period of time. So they will generally look like this. So it becomes very large over a small period of time. So the force is virtually infinite. Okay, it's very hard to say what the force is. But you can calculate the impulse very easily. So if this force stopped my hand, okay, what's the impulse? Yeah, momentum of my hand minus final momentum 0. So negative of whatever momentum I had in of my hand. So it's easier to calculate the impulse, and you can calculate an average force if you like. Okay, if you know how long the collision takes. So the impulse is a well-defined quantity, even if the force is not a well-defined quantity, so to speak. So okay, so we have just put in words what we just said. Okay, so that's why it's useful to define this quantity called impulse. So, for example, now you can solve one of your homework problems that has, or rather the practice problem set problems, which says that there's a ball that hits the wall and bounces off, and you are asked what is the average force acting on it. You are given the time window of the collision. So all you need to do is average force times time window should give you the change in momentum, and that's it. Right? So in other words, it's just like, so the way you would formally solve that problem is to say that average force F times delta T is equal to, so this is average force, integral F dt, right? Because average is just integral F dt over integral dt. So I'm now talking about scalars, so I've also already thought of some direction. Sorry. And this should be equal to change in momentum. Right? So you can calculate the average force as delta average force as delta P over delta T. So nothing profound has happened here. Okay, so that's good. I've said nothing useful yet. So now let's look at momentum conservation. So if I have a bunch of particles, first let's talk about the momentum of a bunch of particles. For if you have a bunch of particles, M1, which has some velocity V1 in some direction. And here's M2, which has some velocity in some direction, V2. There's M3, M3, V3. Let's say M4, V4, so on. Okay. So the idea is that you can define the momentum of the system, which is momentum of the system of particles. And momentum just adds up. Okay. So it's just the sum of momenta of the individual particles, where each particle has momentum calculated as follows. Okay. So you just add up the momenta of all the particles, then you get the momentum of the system of particles. That seems blatantly stupid, but not all physical quantities behave like this. Energy does, momentum does, you know. Not everything behaves like this, so you have to be a little careful. Yeah, okay. So let me leave it at that. So momentum does behave like this. So that's why we explicitly state it. So the momentum of the total system is just the sum of momenta of all the particles. So now let's look at what happens to this quantity. So earlier we said that if there is no force acting on some particle, then its momentum cannot change. But now, suppose there are forces. So let us say there are forces between these particles. So maybe gravity, for example, you know. The particles could be interacting with each other through forces. Okay, so the particles now can be interacting through each other with forces. So if I ask you about any one particular particle, let's say M2, and I ask you if its momentum is conserved, the answer is no, because there's forces acting on it. But if I consider this momentum of the entire system, which I'll call capital P, okay, the sum of all momenta, if there are no external forces, that means forces exerted by something that's not part of your system. So an external force is a force exerted by something outside the system. Then what happens is that if I consider dP over dt, okay, this will give me sum over I, dpi over dt, the sum of the rates of change of all the individual momenta, okay, of the particles, which will give me the sum of the forces acting on each of the particles. Okay, this is the net force on the ith particle, right? But if there are no external forces, for every action force of one particle on the other, by Newton's third law, there's going to be a reaction force of this particle on the other one. So for every force, so let me rewrite this as sum over I and j, I not equal to j, force of ith particle on j. So this is the force exerted by ith particle, by let's say jth particle on the ith particle. I have put I not equal to j in that summation because a particle cannot exert a force on itself. Makes no sense. But for every Fij in this summation, Newton's third law says that there's an opposite force. Says that there is so Fji will be equal and opposite to Fij, right? So Fji is minus Fij. Okay, so in that sum, there will always be terms like, so the sum has terms, sum of all forces acting on all particles of the system has terms like F12 plus F21 plus F13 plus F31 plus F of 2 on 3 or of 3 on 2 plus F on 3 by 2, etc. So all of these forces, these action and reaction pairs will cancel. Okay? So if the only forces acting on these particles are forces between the particles, then for every action, for every force, there's an equal reaction pair on the other side. So when I calculate the net force on the entire system, those internal forces, as we call it, so these we will now term as internal forces because they are internal to the system. So the internal forces cancel. And so we are left with 0. So I get, did I somewhere right? Yeah, okay. So therefore we get the net change in momentum of the system is 0. So this is called momentum conservation. And if I integrate this, I get Pf equals Pi because nothing is changing. Final momentum equals initial momentum. Okay. So momentum conservation is applicable only when you have no external forces acting on the system. Otherwise, if there are external forces, for example, gravity, if you don't consider the Earth as part of your system, gravity is an external force because it's an agency that's outside your system. So then momentum of some particle is not conserved. If I drop something, of course it will speed up. Its momentum is changing. Okay, so because there's an external force of gravity, momentum is not conserved. So if there are external forces that are forces applied by an agency outside your system, then dp over dt, where this is the net momentum, so net momentum of the system, dp over dt is equal to F external. Okay, the net external force acting on it. Total external force. Okay, so hopefully that was simple. Now the question is one of how do you apply these concepts? Okay, so the most useful application of momentum conservation happens to be in analyzing collisions. So remember these two things. Energy is conserved whenever you have no non-conservative forces. Momentum is conserved whenever you have, so mechanical energy is conserved when you have no non-conservative forces, only conservative forces. Momentum is conserved when you have no external forces. Okay, so they're kind of different. You can have, even if you have no external forces, you can have energy loss because of friction, for example. So if you know, my two hands were the only things in the universe, if they came and slid across each other, energy is not conserved, but momentum is. Because the friction dissipates energy as heat. But momentum is conserved because there are no external agencies. Okay, assuming that my two hands were the only things in the universe. When momentum is not conserved, I mean energy is not conserved when every time when momentum is conserved, and momentum is not conserved every time energy is conserved. For example, if I just drop an object, its energy is conserved, gravitational potential energy plus kinetic energy is conserved, but momentum is not, it's speeding up. Okay, so unless I include Earth in the system, momentum will not be conserved. So energy conservation and momentum conservation are different things. They are independent statements and they give you more information when you apply both of them together. Okay, so in collisions, usually what happens is collisions happen, so let's say two things collide, so there is an impulsive force acting between them, you know, changing, because one object cannot pass through the other. The moment the two objects hit, there's going to be a very large force acting on them, and it will move them apart. The problem is you don't know anything about the details of how those forces change. Okay, in reality, what is going to happen is every object, although you would like to believe that it is rigid, you know, will have a little bit of compression, right? So when these two objects hit, the two objects will, try to pass through each other, but they cannot, so they will compress a little bit. So that's more obvious if these were the two objects, because this duster is pretty squishy, so it can squish, right? So when I press them, they will squish a little bit. Okay, but there's only so much they can squish. As they squish, they exert forces on each other, and so they will move backwards. Okay, so depending on how those things squish. For example, if you had clay and you squished clay, it would just change its shape. It would not spring back, right? A piece of clay will just, if you squish it, it will just change its shape. So what happens is that energy that you put into squishing clay went into changing the shape of it and reorganizing the molecules, and part of it just went away as heat. So squishing clay is a non-conservative process. Energy just goes into deforming it and rearranging some molecules and then into heat. Whereas if you squish something more springy, like what's a very good example other than a spring? Oh yeah, one of those those really springy balls. Not so much a squash ball, but something more springy, like those crazy balls that bounce really high. So those things, if you squish them, they will bounce back at you with no loss of energy. Now, what about a squash ball? A squash ball does come back. It does spring back, but it will lose some energy into heat in the process. So if you play a squash or racquetball, you'll see that eventually that ball will get heated up, and that's because it's losing some of the energy that went into compressing it. So if you push it, this far, it might slowly relax. It won't turn all of that energy into like kinetic energy, and so it's not going to return all of its energy. A spring, on the other hand, if I just have springs on something, a bumper that's made of a spring, it will just compress and return back all the energy to me. So, so depending on the nature of these materials, there are two kinds of compressions that you can have in a collision. Okay, so depending on the nature of the material, two kinds of compressions or so one is called, there are two kinds of collisions corresponding to these two different natures of the materials. If things are springy and if things are springy and there is no loss of energy, so imagine that you have masses with springs attached to them and they come and collide. Then whatever energy went into compressing these objects is returned back into mechanical energy. These things are called elastic collisions. So elastic collisions are where the energy that goes into compressing the objects is returned back as mechanical energy. So in some sense, you have springy materials. And this also means that energy is conserved. So I'll put emphasis on mechanical energy is conserved. So in these kinds of collisions, mechanical energy is conserved. Then there's another kind of collision, which is an inelastic collision. For example, if you have clay-like objects, objects that are not springy, thingy and lose and dissipate, let's say, some of the energy put into them, as heat, sound, whatever. Or absorb it in changing the shape. So for example, if you put energy into, if you try to put energy into clay by compressing it, it will just change its shape. So those are inelastic collisions. And in this case, mechanical energy is not conserved. And so we can't use energy conservation because we don't know how, unless you know the details of how this thing eats up energy when they collide, unless you know lots of details about the material, you can't use, you don't know how much energy is lost. So there's no easy way of handling these collisions. So unfortunately, almost every collision that you see in real life is somewhere in between these two cases, or is usually inelastic. Okay, some part of the energy is not conserved. Okay, so elastic collisions are rare. Of course, you can find collisions that are approximately elastic, and I guess billiards will be fairly elastic. For example, there was this weird game where you hit discs with other discs, and they had exactly the same masses. Now in billiards, you have to in pool you always have to have the white ball more massive than the rest of the balls. Otherwise, the cue ball will actually just stop when it hits something else and exchange its momentum. So it's kind of boring. But there was this funny game, I don't know what it's called, where everything had equal mass, and so what is it called? Shuffleboard. So let's go look at it. Oh wow! It dropped me off the internet. Let's. Sorry, it'll take me a bit to connect to the internet. Like shuffleboard? Is that what you said?
I think so.
Okay. So let's see. Maybe that's what it is. So I've never seen that game anywhere except that one place that I saw it at. So it seems to be pretty popular though. Let's see. Yes, that does look like what I'm talking about. Yes. Yes, precisely. So when one puck collides with another, it just stops and the other puck takes its momentum, right? Yeah, okay. So I think that thing is pretty elastic. It's designed to be pretty elastic because they virtually exchange speeds. So that would be a good example of something that is almost elastic collision. Whereas the intermediate cases, like maybe a squash ball, are just really hard to handle. You need to know what is called you can define various things, and you can invent a quantity called the coefficient of restitution and use that to account for how much energy is lost. But how will you calculate that coefficient of restitution? You will have to do some experiment, and then it works only for that one object that you found. So it's just some fudge factor that you throw in from that you can calculate from experiment. So that's kind of boring. Unless you're, if you really need to use it, then you look up the coefficient of restitution and you can handle inelastic collisions. But usually the cases that are easy to handle without any details of the materials are very close to perfectly elastic, like maybe a shuffleboard, and very close to perfectly inelastic. So there's also the other extreme where that's a little harder to understand. So I will talk about it in a bit. So the energy that goes into compressing this object the maximum energy that you can go into compressing these objects is the relative kinetic energy. So so if I'm in the reference frame of one of these objects, then and then this is just coming to me, and I'm sitting stationary in my reference frame. So it comes with some velocity, which is the relative velocity, and let's say it just stops, okay, because it compresses, and then they kind of stick together because it's like two pieces of clay. So let's say I am a piece of clay and I'm moving along with it, and so as far as I'm concerned, this piece of clay is stationary, and the piece of clay comes and hits this piece of clay, and then clay is sticky, so it will just stick, and in my reference frame, that's it, it's just stopped. Okay. So what happened in this if I analyze from my reference frame, what that means is all the kinetic energy that this thing had is just gone, is just dissipated away. Now if I'm in the reference frame of the ground where this piece of clay is moving and this piece of clay is also moving, whatever it is, that's the maximum amount of energy that can be dissipated. Okay, because I just analyze it from that reference frame. I don't have a very good intuition, but you see that's the maximum amount of energy that can be dissipated. That's the energy in the relative motion. Okay, so that extreme is called a perfectly inelastic collision. So there's the perfectly elastic collision where energy is all conserved. The other is the perfectly inelastic collision where these objects stick together and move with the same velocity. So all the energy in the relative motion is just dissipated away. Those are the two easy things that you can handle physically without knowing any more details about the objects themselves. Otherwise, you need to know how much of the energy is gone in compressing these objects. So you need this coefficient of restitution. But I think in this class, I don't know if they introduced the coefficient of restitution. But generally, I don't like it, so you won't see many problems on it. So we will handle two approximations. Okay, so most collisions are partially inelastic. That is, some of the energy is dissipated away. These are hard to analyze without properties of the materials. Okay, so we will stick to two approximations. One is perfectly elastic, where energy is conserved. The second one is perfectly inelastic, where all energy in the relative motion is dissipated. So maybe I should put kinetic energy here. And the relative motion is dissipated. And this is called perfectly inelastic. In other words, if this happens, if all the energy in the relative motion is dissipated, then they have to move with the same velocity. So the objects stick together. Okay, so objects move together at the end of such a collision. Okay, in the perfectly inelastic case. Okay, so let's first talk about perfectly elastic collisions. This is going to be a little bit of a mess, but bear with me. We will simplify the equations at the end, and then it will become much more simple to understand. So inelastic collisions are very easy. The perfectly inelastic case is very easy. The math is all extremely easy because they stick together, so they move with the same final velocity. The perfectly elastic is a little trickier, but once you get some intuition for it, it will become much easier. So we'll do that. So here's a perfectly elastic. So let's analyze the perfectly elastic collision first. So in all of this, I'm going to assume that external forces are not present. So there's no third party that's pulling all these objects strangely. Now, there's always gravity. So what do I do about the collision like this? How do I analyze, how is this approximation valid? I'm going to say that there are no external forces. Why is that okay if these two things are colliding like that? Yeah, gravity is acting downwards. It won't change the momentum in this direction. So I'm allowed to conserve momentum in this direction. Now, does it mean I cannot handle this? Okay, like where both are going vertically up? Because now gravity is along the direction of momentum. It will change the momentum. How would I handle that? Can I handle it at all? The answer is you still can handle it because of the following thing. Gravity is a constant force, which is some m times g. Okay, it's good. It's there, but it's not really strong. Compared to the impulsive force, when this compresses, there's a huge force, right? Compared to that force, gravity is so small. So as long as the time of collision is fast, okay, such that the impulse delivered by gravity is negligible, then only this internal impulsive force will deliver any impulse. So I can neglect the impulse delivered by gravity over the short duration of the collision. So you can still apply conservation of momentum, but you have to be cognizant of the fact that it's an approximation as long as the collision interval is really short. So the forces are really impulsive. Okay, and the moment they stop, so far you can conserve momentum, but the moment they fly apart, you again have to include gravity because gravity is now going to act and slow it down. So for the short time of the collision, you can neglect gravity's presence as long as the impulsive forces are much stronger than gravity. So sometimes you will use momentum conservation even when you technically cannot in a collision because the impulse delivered by external forces like gravity is negligible. So that's just a statement now. We will talk more about it later. Okay. So let's consider two objects, mass m1, speed v1. Let's start with one dimension. Okay, so all of these will be 1D, no external forces, or no or negligible, let's say. So m1 has velocity v1, m2 has velocity v2. I'm not going to bother writing vector signs because it's 1D, and then so by the way, these 1D collisions are called head-on collisions because they collide head-on. So 1D is head-on. So these velocities are signed scalars, plus positive and negative scalars. So I'm going to choose this maybe as my positive direction, positive x. And let's write the total momentum. So this is initial situation. They are not collided. They have this setup. So initial momentum is P equals m1 v1 minus m2 v2. So I'm assuming that this is a magnitude. This is not a magnitude. Okay, in the sense it's a positive number. That's why I've accounted for the sign. I've accounted for the sign here. Okay, so this is initial momentum. And the final case is, these two collide. So something happens during the collision that we don't know anything about, except we know that whatever forces cause the collision are internal forces. So we can apply momentum conservation. Okay. So m1 later flies off with v1 prime. Note the directions. I'm going to stick to these direction conventions. And again, these are magnitudes. So this is a positive quantity. So the final momentum is m1 v2 prime, sorry, m1 v1 prime with a negative sign plus m2 v2 prime with a positive sign. Okay. So now if I conserve momentum, then I get the following equation. So this is conservation of momentum. So I get m1 v1 minus m2 v2 equals minus m1 v1 prime plus m2 v2 prime. Now let us say I know the initial velocities v1 and v2 of the collision. The idea in this collision is usually I know the initial velocities, I know the masses, I have to find the final velocities with which they separate. Okay. However, I have only one equation but two unknowns, v1 prime and v2 prime. So I need another condition. Just momentum conservation alone will not help me solve the collision completely. In this case, it's perfectly elastic, so let's apply conservation of energy. So final energy equals initial energy, or whatever the other way. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Notice that the energy doesn't care about the sign, doesn't care about the direction, right? It's a scalar quantity, so it's plus all through. Equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, so look at this. We have now two equations and two unknowns. Okay, the unknowns being v1 prime and v2 prime, and the equations being those two: energy conservation and momentum conservation. So let me cancel out this half. Okay, all through. But you see, it's a mess to solve, right? Look at that. It looks so messy. However, there's a trick to solve this, and I'm going to try and do that on the spot. Although I don't remember the trick, really. Let's see. So I think it involves doing the following. Okay. So let's move some terms around. Let's rewrite this as m1 v1 squared minus v1 prime squared equals m2 v2 squared minus, sorry, is v2 prime squared minus v2 squared. So I just rearrange 2. Okay, and get that. And rearranging 1, I have the following equation. So this comes from 2, this comes from 1, m1 times v1 plus v1 prime equals m2 of v2 prime, okay, v2 plus v2 prime. Okay, now I can use an identity that we all know, a squared minus b squared is a plus b times a minus b, to simplify equation 2 as follows: m1 times v1 minus v1 prime times v1 plus v1 prime equals m2 times v2 minus v2, v2 prime minus v2 times v2 prime plus v2. So I get this, and now I can use 1 in this form of 2, which I will call 2 prime, to get the following. So m1, so m1 times v1 prime plus v2. So I'll just replace this with that. Okay, so using 1. So then I get m2 times v2 plus v2 prime times v1 minus v1 prime equals m2 times v2 prime minus v2 times v2 prime plus v2. And you see this cancels. And the m2 also cancels. So I am left with the equation that says v1 minus v1 prime equals v2 prime minus v2. Or in other words, v1, why am I not getting the sign correctly? Did I do this right? Or have I missed a minus sign somewhere? I think that's right. Okay. Yeah, okay, this is correct. Because of the way I chose my conventions, that's right. Okay, I'm getting the right thing. It's v1 prime plus v2 prime. So let me copy paste these diagrams so that we remember how we define V1 and V2. Okay, so copy, paste. Okay. So if you see what this means, this is giving you one equation. Okay, this is just a simplified form of energy conservation. When I use momentum conservation to simplify the expression for energy conservation. What this is telling you is the velocity of approach, velocity with which these two are approaching each other is the sum of the velocities. So for example, if I were sitting on this, I would see this guy come at V2 plus V2. Right? It's just a relative velocity. So this is the relative velocity of approach, is V1 plus V2. This is the relative velocity of recession, how fast they are moving apart. So for example, if I were sitting on this ball, then I would see this moving with V2 prime plus V1. Okay? So this term is the velocity of approach, and this term is the velocity of recession. So what this is telling you is velocity of approach is equal to the velocity of recession. So for an elastic collision, this is true. The velocity of approach is equal to the velocity of recession. So the easiest way to solve elastic collisions is, instead of writing out energy conservation, it's easier to remember this and write energy conservation. Write momentum conservation. So this statement so this principle, along with momentum conservation, gives us the solution. So let me just write out that solution. So we have V1 prime plus V2 prime equals V1 plus V2. This is velocity of approach equals velocity of recession. The other one is M1 times, let me just copy that as it was, M1 times minus M1 V1 minus M2 V2. V1 minus M2 V2 is minus M2 V2 prime plus M1 V1 prime. And so we can just simplify these things, and I want to do it for a particular reason. Okay, no, let me not do that. So I'll just say can solve this system of two linear equations in two unknowns for V1 prime and V2 prime. So that's straightforward, right? Okay, so you can cross multiply and solve things and so on and so forth. But let me analyze a certain special case. The special case being that M1 equals M2 equals some M. Okay, so let's call this equation 1 and this equation 2 now. Then 2 becomes V1 minus V2 equals minus V2 prime plus V1 prime. Okay, so I just cancel out, since M1 is equal to M2, I just cancel it off all the way. This gives me this following simple equation. And this, along with 1 is also true. V1 plus V2 equals, so let me just write it as follows. V1 prime minus V2 prime equals V1 plus V2. So these two equations, as you can see, just tell you that V1 prime, sorry, I missed some sign somewhere. Not getting the answer there. Okay, well, yeah, okay, I think it's okay. Let's see, maybe I missed the sign. this is true. Velocity of approach is velocity of recession. Did I write this correctly? Oh, you know what? I wrote momentum conservation wrong. This should have had a positive sign. This is a negative sign because v2 prime I've chosen in the positive direction, v1 prime in the negative direction. So that was my goof up. Okay. So now that that's fixed, this will give me wait a minute. So this will give me v2 prime minus v1 prime. Right. Okay. Oh, sorry. No, sorry, I corrected the wrong equation. This is the equation that I had to correct. That's hold on. Oh yeah. Now 2 is momentum conservation. So yeah. Okay. So yeah, I had a sign mistake here, which I corrected and transferred here. So that's that equation. Now, if you see what happens, add 1 and 2 together, and you'll see that 2v1 equals 2v2 prime. Okay, which will give me v1 equals v2 prime. And then if you subtract the two equations from each other, you will get so 1 minus 2 is what I said I'll do, right? So 2v2 equals so minus, I'm subtracting this from that, so therefore 2v1 prime, or v2 equals v1 prime. So they just exchange velocities. So if you have an elastic collision between objects of the same mass, they exchange velocities. So this is the shuffleboard game, okay, that we were talking about earlier. So the masses of all the strikers or all the pucks are the same. So when you strike one with another, they just exchange velocities. So if one is moving and the other is at rest, then the other will start moving. So the idea is if I have two masses that are equal and the collision between them is elastic, if I have one mass come and hit the other, they will just exchange velocities like this. Okay, so you might have seen this as a physics example, for example, Newton's cradle. Another example is, Newton's cradle. So this also tells you that the mass of a pool ball, like the cue ball in billiards, needs to be higher than the mass of the other balls, so that although it collides, it keeps moving. Otherwise, the cue ball would stop when it collides, and then it would be a little less interesting game because you can't do rebound. I mean, you can't do interesting things like strike two balls simultaneously into the pockets. The other thing to note is, although you might study all of this about collisions, that doesn't make you better at pool. So physics is helpful in knowing the basic behavior of these games, but not more than that. So those are important aspects of perfectly elastic collisions. Once you simplify energy conservation to the form of velocity of approach equals velocity of recession, it's really easy to solve these problems. But inelastic collisions are even more easier because there is only one unknown. Perfectly inelastic, I should say. It's not general inelastic, but perfectly inelastic. Sometimes we just call these inelastic collisions. So in a perfectly inelastic collision, if you have the two objects, so M1, M2. So M2 is like a piece of clay, let's say. And let's say this guy is moving with V1, this guy is moving with V2. Right now I'm just going to change, let me just do this. It's okay, V2. And this will be my positive x-axis. And again, these velocities will actually, these are not signed quantities, but the magnitude, so I'll just include the sign in my calculations. Okay. So if this is the initial situation, let me relabel these, please, so that M1 goes with V1. In the final situation, this is a perfectly inelastic collision, so the objects have to move with the same with the same velocity. So in some sense, I'm thinking of M1 like a piece of clay which just deforms and sticks to M2. So in the final situation, you just have mass M2 with a blob of clay M1 attached to it. Okay? And both of them are moving with speed, V, maybe that way. V final, or I'll just call it VF for V final. Okay? So objects stick to each other. Which is saying the same thing as all the velocity in their, all the kinetic energy in their relative motion is dissipated away. So they now are moving together. So in this case, energy is not conserved. Okay. Let me just remind ourselves of that. But momentum is, as long as there are no external impulsive forces, momentum is conserved. And so I can write the total initial momentum, m1 v1 minus m2 v2 equals minus m1 plus m2 times v final. Okay. And so then I can calculate v final very easily. M1 v1 minus so it's m2 v2. I'm just taking that sign in, minus m1 v1 over m1 plus m2. Okay. So that tells you what the final velocity of the system is. So this is very easy to calculate. You can also calculate loss. Now that you know this, now that you know the final velocity, you can ask what is the loss in energy. Okay? And that should be 1/2 mv final, sorry, 1/2 of m1 plus m2 times v final squared minus 1/2 m1 v1 squared minus 1/2 m2 v2 squared. So this is just final energy minus initial energy. Oh, I should do the other way if I want loss, but this will give me some negative answer, so it doesn't matter. Okay. And so I can simplify this by plugging that in, and then I see 1/2. What I have is m2. So 1/2. So one of these, when I plug this in here, one of this m1 plus m2 in the squared, when I have to square it, so one of the m1 plus m2's cancels with this. So I am left with an m1 plus m2 in the denominator. And in the numerator, I have m2 v2 minus m1 v1, the whole quantity squared, minus 1/2 m1 v1 squared minus 1/2 m2 v2 squared. So you can expand the numerator or whatever, and then you get some junk. I think it's not going to simplify nicely. So I'll just leave it at that. Actually, no, it might be worth simplifying because I should be able to explain. Yeah, so let me simplify this, although it seems very painful. Is it worth simplifying when I learn something? Okay, I'll do it anyway. Let's see if we learn something out of it. m2 v2 squared minus m1. So this is m2 squared v2 squared plus m1 squared v1 squared minus 2 m1 m2 v1 v2 over m1 plus m2 minus, I'm taking the 1/2 out, so this is minus m1 v1 squared minus m2 v2 squared. I hope I can simplify this. I want to get how do I get that? Oh, you know what? It's not going to simplify to anything nice. So let me leave it at that. Okay. I thought it would, but no, it will not simplify to anything nice. Unless one of the masses is much higher than the other. So let's just leave it at that. So you can calculate the energy loss if you know the final velocity. So that's it. That's everything about one-dimensional, that is head-on momentum, head-on collisions and momentum conservations. Let me just say something about 2D collisions. So momentum is now, remember that momentum is a vector quantity. So you can conserve momentum as a vector. Can conserve so for example, you will write Px initial equals Px final, and Py initial equals Py final. So you can write two equations. But in a two-dimensional collision, you will have four unknowns at the end of the day. Two components of the velocity of one object and two components of the velocity of the other object. So you have four unknowns, and if it's inelastic, then if it's inelastic, then you have two unknowns and you have two equations. So you can solve it completely. So if the two objects stick together, then these will give you two equations. The two unknowns are the velocity of the final blob that moves together. So you can solve perfectly inelastic collisions in 2 dimensions. Okay. But if you have a perfectly elastic collision, then you have two equations plus energy conservation, so 3 equations. But you will have 4 unknowns, the 4 final velocity components. So there's no way to solve it. You need to know something more about the details of the interaction and things like that. You need to know, you cannot solve it without knowing exactly how this object is interacting with the other. Okay, so if the collision is not head-on and it's 2-dimensional and it's elastic, you'll need to know all the details of the interaction to solve this. And in fact, this is what this is kind of why such collisions are a big deal, because you can actually, if you do an experiment involving such collisions, you can find what the interaction is. So you can find the details of the interaction if you know how objects behave under this collision. And so, in fact, this is what people do at the LHC and all these particle colliders. Right? They're colliding pairs of particles to find out how they interact, so you can get some details about the interaction. And I mean, the first such experiment, so these are called scattering experiments. The first such experiment was Rutherford's, what's that called, alpha particle experiment, where he had a gold foil and then he shot alpha particles at it, and he saw that they scattered wildly. That told him that there's a central charge in the atom that's the nucleus, and there's concentrated charge. So it told you something about how the electrostatic interaction occurs and things like that. Although in this case you knew something about the electrostatic interaction, so you could predict that there was this condensed blob of charge. So 2D elastic collisions are hard. 2D inelastic collisions, you just write these two equations. You have two unknowns and you can solve it. So let me just make a note of this. Two unknown final velocity components. And two equations, two components of momentum conservation. So I think there is one problem on the practice set like this, where you're asked to find some angle. It's very straightforward. Whereas 2D elastic collisions need information about the details of interaction. Four unknown velocity components. And 3 equations. Two from momentum plus 1 from energy. So I'll just leave it at that. Okay, so you can't just conserve kinetic energy and solve these problems. So in fact, you use these to find out more about the interaction. Okay. So that's it. That's kind of all I have to say about momentum and collisions. So I'll leave it to you as to what we will do through the rest of. So if you want to solve some of the problems in the problem set, I can do that. If you want to go over the exam, I can do that. Or if you want to talk about center of mass, I did that yesterday, but I can still do that. Whatever.
So what the exam have the solutions been released? Have the solutions been posted yet?
No, I haven't posted solutions yet. I think I might be able to make them. I don't know if I can make them available before I make this course available. I guess I can, so let me do that. Oh, but Quest doesn't know which version you got, so no. I don't think I can do that. Yeah. Yeah. Yeah, I need to scan them. I'm going to try and scan them tomorrow. Okay. Otherwise it will have to be during spring break.
Okay. And also, center of mass. There's an example problem in the book. Could we go over that? Because I have my
okay.
book.
Yeah, I'll need your book because I haven't really looked at it.
So finding the center of mass of the pyramid is really interesting.
Oh, okay. Just complete this video segment so that